Good morning, everybody. Well, we've got a few minutes left, so we've got to wait for a few more minutes before we begin the lecture. In the meantime, if there is any question or something that I can answer or explain, please go ahead with your questions in regards to, say, the test for next week or anything else. Is there any questions? No questions? Okay. So you can enjoy yourselves for a few minutes. Okay. Good morning again. The number of people participating in lectures is going down and down, session after session. So I assume the way it is, in a couple of weeks, we will have only a few people sitting in the first row only. I hope that doesn't happen, but anyway, that's the way we are moving to. Is it the same for the other lectures as well? Participation. Is it solo in other units? Similar. Well, it's in the middle of the semester, so you will have more participation in the beginning of the semester and also at the end. That's the way it is. Okay. Well, in last week's lecture, we did talk about turning operation and also drilling. What was the difference between the two, turning and drilling operations? The main difference between the two metal cutting processes. Well, the main difference between the two. turning and drilling. In turning, it's the workpiece which rotates, and the cutting tool is stationary and only makes a linear motion, which is called feed, right? And there is the type of the cutting tool which is used is a cutting tool with a single cutting edge, right? How about drilling? In drilling, it's the cutting tool which rotates, and it is the workpiece which is stationary. Which one has got the feed motion then? The workpiece or the cutting tool in drilling? It's the cutting tool. So in drilling and also in turning, it's the cutting tool which has got the feed motion. However, in turning, it's the workpiece which rotates. In drilling, it's the cutting tool, right? Okay, good. And the number of cutting edges in drilling is often 2. In turning, it's 1, right? That's the other difference between the two. Now we are going to talk about another widely used machining operation, which is called milling. Well, in milling, as we can see in this slide, it's the cutting tool which rotates, similar to drilling. And it's the workpiece which is stationary. In drilling, it was the cutting tool making the feed motion. How about in milling? It's the workpiece. So it's different from the previous two operations. In turning and also in drilling, it's the workpiece it's the cutting tool which makes the feed motion. However, in milling, it's the, did I say it incorrectly? In turning and also in drilling, it's the cutting tool which makes the feed motion. In milling, it is the workpiece, okay, which is on the table. As you can see, the feed motion is being applied to the workpiece, which is different from the previous operations that we had. And also the other characteristic of milling operation is that we've got multiple cutting edges on the cutting tool, making it different, very different from turning operation. And also the axis of tool rotation, as mentioned here, the axis of tool rotation in milling is perpendicular to the feed. This is feed motion, and this is the axis of rotation of the cutting tool. As you can see, it's perpendicular. And in that one as well, that's the axis of rotation, and that's the feed motion, which is perpendicular. And these are two basic milling operations: peripheral milling and face milling operations. What's the main difference between these two milling operations? What surface is cutting the face, which is right? In other words, we can say the axis of rotation of the cutting tool. In peripheral milling, the axis of rotation of the cutting tool is parallel to the surface being machined. However, in face milling, the axis of the rotation of the cutting tool is perpendicular to the surface being machined. And this makes a big difference in the structure and configuration of the machine which is being used in order to perform the task. What does this mean? It means that, is everyone listening? Please do not talk to the person sitting next to you, because it does disturb other people sitting around you. Okay. These two operations, any operation which is similar to this, where we have got the axis of rotation perpendicular to the surface being machined, is it can be performed on a type of machine tool which is called vertical milling machine. Meaning the axis of rotation of the cutting tool is vertical. And any cutting tool which requires a rotation along an axis parallel to the surface milling machine can only be performed on a different type of milling machine, which is called horizontal milling machine. The whole structure of the machine is totally different. Meaning that if you've got a horizontal milling machine, then you cannot perform this task on it or the other way. In the workshop, we've got two milling machines. The ones that we have got in the workshop, those who have done the activity on the milling machine. Could you please help me to identify the one which is similar to the one that we have got in the workshop? Is it A or B? The ones that we have got in the workshop are similar to A or B? Anybody who has done the milling activity in the workshop? Nobody? Which one? A. It's B, I would say. It's B. If you do the activity, you notice that, you will realize that the cutting tool rotates just like that, not like this on the machine. So it is vertical. And vertical milling machine is much more popular in industry. Reason, I would say, it gives you more freedom of the selection and choice of the milling activity. However, horizontal milling machines often do provide us with a higher rate of material, a higher material removal rate, the horizontal ones. So, if we are after productivity and the type of the activity that we want to perform can be performed on the horizontal milling machine, it's often the type of the machine to be chosen. Otherwise, vertical milling machine is preferred if we have no idea of the type of the operation to be performed on the machine. And the equation given here is the equation which relates the cutting speed to the spindle speed. Is this familiar to us, this equation? It is. It's very similar to the one that we had for turning. It's exactly the same equation. And also drilling. The same equation is used in order to relate, say, spindle speed, cutting speed. The only difference being the parameter. In turning, D represents, capital D represents workpiece diameter. In turning, in milling and also in drilling, it represents the diameter of the cutting tool. That's the only difference. Okay? And also please note that because the unit for V is meters per minute, we've got to substitute the diameter of the workpiece or the cutting tool in meters in this equation, this is often given in millimeters. So we've got to do the conversion of the unit, or if it is in millimeters, divide the whole equation by 1,000. Okay? So take care of the units in order to get the right values. I beg your pardon? For both it's the same. Same equation applies to any machining operation, I would say. Any machining operation, drilling, turning, this operation or that one is the same. Indeed, cutting speed is defined as the distance traveled by the cutting tool on the surface of the workpiece, which is the same. Okay? Thickness is not mentioned here. We are talking about cutting speed, which has nothing to do with thickness. It's important when you are computing material removal rate, which isn't of concern in this equation. Okay? Well, there are two common types of milling operations, as you can see here. Conventional milling versus climb milling. And what's the difference between the two? What's that?
The tooth angles. the angle of attack of the teeth.
The main difference indeed, the most say evident difference between the two. There are differences. The most evident difference, which causes some other differences in other parameters, is the feed motion. The rotation of the cutting tool is clockwise in both. However, take a look at the feed direction on the one in conventional milling and the one in clamp milling. Okay, that's different, isn't it? Okay, can we make use of any of these two methods in order to cut the material? Yes, we can. Which one is preferred?
The conventional.
The conventional. And have you got a reason for that?
It's got a long squeeze.
Think about it and talk to your partner about this. I'm going to tell you the difference between the two, which is very important to realize the difference between the two methods. And I would say it's possible that you will have a question on this in the final exam or maybe in the mid-semester test event. Okay, because it is important to understand the difference between the two. Try to figure out what are the advantages or disadvantages of each of these two methods compared to one another. But what I can tell you is that both methods are being used in industry because of the advantages that each one of them has. Then, can I ask you to share your findings with us, please? Anybody who wants to share his findings with us, please raise your hand. Well, okay, go ahead.
Chip length is longer.
Correct. Chip length in this one is longer, which is very obvious. Okay, what else? Yes? Hardness of the metal, what do you mean? It's the same material which is being cut in this given example. We are considering that we are machining the same material, okay? So the workpiece material and the cutting tool material is not different. Okay, what else? Yes?
I think it was a tool like a cutting tool. Maybe because the way of cutting to the workpiece is different. So maybe in the left one, the tool of the cutting tool is longer.
Correct. Correct. Let me show you the specifications of the one in conventional milling. Look at this, please. We've got the need for more power here compared to that one, and that one as well. More power is needed in this compared to that one. This one tends to lift the workpiece. Look, the cutting tool is taking the cut from the bottom and tends to lift the workpiece from the table. But in here, it's pushing it on the table, so it's not lifting the workpiece. In this one, we've got a smoother machining, meaning that there is less vibration and less noise resultant from the machining operation compared to this one, which makes a lot of noise and vibration. Is it desirable to have a machining operation which is making a lot of noise and vibration? Of course not. And that one, as a consequence, because it provides us with smooth machining, this operation is used in order to produce a surface which has got a smoother surface, or its surface finish is higher compared to that one. Now, however, please note that in here, which makes a lot of noise and vibration, we achieve a longer tool life, making this a very actually important advantage. And that's one of the reasons that we do not actually forget about this method and still make use of it. What explains this? Longer tool life in that one. What explains this? Yes?
I actually wanted to ask, is that the tool that you're making or the tool that you're cutting that lasts longer?
I beg your pardon?
Does the cutting tool last longer? Or
The cutting tool. The cutting tool. Yeah.
Because it doesn't touch the material as much.
It doesn't crash the material.
Sheet length is less.
The length, yes, the period of the time when it is in touch. That's what you're trying to say,
Yeah.
right? Look, when this one is taking the cut, first of all, the thickness of the material is maximum in the beginning of the cut, and as the cutting progresses, the thickness of the chip actually is reduced, and at this point, it's 0. Only in a small fraction of the rotation of each cutting edge, the cutting edge is in touch with the workpiece and is taking the cut. Compare it with this one. There is a longer period of time in a given rotation during which a single cutting edge is taking the cut. And those who are post-grad and they are doing, we had a presentation last week talking about tool life. Tool life. Tool life is a function, it can be defined as the time during which the cutting tool is taking the cut. In here, in each rotation, for a longer period of time, the cutting tool is taking the cut compared to this one. So in here, there is this amount of time during which the cutting tool is taking the cut. So tool life in here will be longer than that one. Reason, in here, the cutting tool is taking the cut for a shorter period of time compared to that. As a consequence, your cutting tool here lasts longer. Of course, here we have got more vibration. Reason is that we start with taking a really big cut in the very beginning, a really big cut. So it results in vibration and noise. In that one, the thickness of the chip which is being produced starts from 0 and gradually it increases. So it results in a smoother cutting, less noise and less vibration. As a consequence, because economy is important for us, economy, and we want to make the cutting tool last longer. We take the rough cutting with this one, making the cutting tool last longer and produce more workpieces. And as this method does produce a rough surface, we take the very last cut in this method in order to produce a smooth surface. Okay? So this one is used for roughing operations, and that one is only used for finishing operations. So that what we get is a combination of reduced cost of tooling and improved productivity and quality surface finish. That's what we get when we make use of the both methods in combination. Okay? Good to know. Any questions on this? Okay, let's move on. Say that again.
So which one is better?
Well, hard to say. Hard to say. We've got to make use of the combination of the two. Reason, you cannot say definitely this one is better than that one. This one has got its advantages, that one has got its own advantages. The best method is to make use of the combination of those ones. Make use of this one for rough cutting, take a number of cuts, and when the material is very close to the final size and geometry, take the very last cut, making use of that one. Okay? The combination of the two gives us the best result. Okay? Clear, everybody? Good. Okay. Moving on. I know that I have made a question on this. I don't know in the for the mid-semester test or for the final exam, but I'm sure that there will be at least one question or maybe two questions from comparison of the two methods. So it's a good idea to actually spend some time on this study and understand the concept properly. Okay. Peripheral milling, where we've got the axis of the cutting tool parallel to the surface being machined. As you can see, depending on the type of the cutter and depending on the number of cutting tools, we can produce different types of surfaces. Choose the combination, the type of the cutting tool and also the number of the cutting tools in a way that it gives you maximum productivity. Sometimes, as you can see, we can, on horizontal milling machines, we can make use of a number of cutting tools instead of one in order to increase productivity. And sometimes we can make use of 4 milling cutters in order to, again, reduce required machining time. Of course, the cost of tooling in this type of machining is more than the other ones. In other words, sometimes we can ask tool manufacturers in order to produce a cutting tool with a specific shape and geometry for a given part, which is specifically designed and made for that given part only. It's not a standard tool. It is a custom-made tool which is made only for particular customers. And here we've got a number of other milling operations similar to face milling operations, as you can see. Where the axis of the cutting tool is perpendicular to the surface being machined. As you can see, there is a variety of machining operations, milling operations that can be performed by making use of this type of machine tools, which are vertical milling machines. Face milling, end milling, slot milling, contour milling, pocket milling. This type of operation is called end milling. These are end mill cutting tools, these four, and these ones are called face milling cutting tools. And that one, which is often used on a CNC machine, and as you can see, the tip of the cutting tool has got a spherical shape in order to be used to produce curved surfaces. If you make use of a typical cutting tool like that to make this, what happens is that you produce a rough surface here. In order to produce a smooth curved surface, we've got to make use of, say, spherical cutting tools to improve the surface finish, resultant surface finish. And here we can see a high-speed milling operation where a really large diameter cutting tool, which is called a face mill, is used. And the diameter of these cutters starts from 3 inches, which is 7.5 centimeters, up to 3 feet, which is roughly 1 centimeter in diameter. They could be really large in diameter, really large. And in order to increase the speed of cutting, some indexable inserts are used, which are adjusted on the face of the cutting tool. That's why this is called face milling. The face of the cutter is taking the cut. And the cutting speed which can be used when we are making use of indexable inserts is 2 to 3 times greater than high-speed speeds. That's why this is called high-speed machining operation. And here we can see the drawing of 2 typical say milling machines, as I mentioned. Here we've got vertical milling machine, which is also called vertical knee and column milling machine. As you can see, the axis of rotation of the cutting tool is perpendicular to the surface milling machine. And that's the type of the machine tools we have got in the workshop. And in here, the axis of the rotation of the cutting tool is parallel to the surface milling machine. We've got an arbor, and that does provide us with the possibility of inserting more than a single cutting tool on the arbor in order to increase the area, the width of the area of the machine at a given time. As I said, this one is much more popular than that one, but that one is also being used widely. So the distinguishing feature of the two machines is the axis of rotation of the cutting tool. Okay? That's the distinguishing feature of the two. Let's play a video clip on milling machines, and then we will continue.
Face milling cutters effectively generate flat surfaces at high speeds with the spindle axis perpendicular to the work surface. Face mills range from about 3 inches to 2 feet in diameter. In face milling, the cutter body has multiple pockets to accept a variety of insert types. Metal is removed by the peripheral edge of the insert, and its bottom edge cleans up the work surface and produces the surface finish. Milling edges, shoulders, and grooves may use a combination of end, peripheral, and/or face milling operations. Edges may involve 1 or 2 surfaces, and the operation may be called edging. Shoulders typically have 2 surfaces. Grooves usually have 3 surfaces and may be closed at one end or open at both ends. Grooves may be cut on internal and external flat surfaces as well as round surfaces. Peripheral milling cutters have cutting edges on their periphery which are parallel with the axis of rotation. Peripheral milling is advantageous for long open slots and forms. End mill cutters are round shank tools with cutting edges on the periphery and end. The axis of rotation is perpendicular to the surface produced by the end of the tool. Its size is measured by diameter and cutting depth capability. Since end mills cut more with the teeth on their periphery than with the teeth at their end, they are susceptible to lateral forces. This makes them subject to deflection, which reduces the accuracy of the piece milled and can lead to tool breakage. Short, shallow slots are often done with end mills. Deep, narrow slots may be milled with an end mill, a thin slitting cutter, or a grooving cutter. Grooving or slotting cutters are generally more efficient than end mills in cutting long and deep slots because of their larger diameter and greater number of teeth. Chamfers may be produced with the chamfering end mill, which breaks the sharp edges of the workpiece with a 45-degree angle cut. Chamfers can also be generated using end mills, form peripheral milling cutters, long edge cutters, or face mills angled 45 degrees to the work surface.
Okay. I mentioned the maximum diameter of the face mills, 3 feet. It was mentioned 2 feet in the video clip. Which one is correct? Which one? Both. Reason? If you are after a standard face mill, what you can find in the market is up to 2 feet in diameter. But you can order actually the customized cutting face mills, which could be up to 3 feet in diameter. You cannot find them in the market, but they can make it for you if you want to. Larger than that has not yet produced as far as I know. Okay? So if you need that one, you've got to request for that one to be designed and made for your application, which I have seen it in an industry being used in this diameter. Okay. Now let's do an example problem on milling. Well, here what we can see in this figure is a peripheral milling operation. The dimensions of the part are given, which we've got a flat workpiece. It is 400, well, it must be in millimeters, which is a minute. Let me have it corrected just now. It must be mm. Okay. It's 400 millimeters long and 600 millimeters wide. 460, not 600, 60 millimeters wide. The milling cutter has got a diameter of 80 and it has got 22 cutting edges. 22. And the width of the workpiece, of the cutting tool is Why the length of the cutting tool is longer than the width of the workpiece. Meaning that once you take a single cut, the whole surface will be machined. Cutting speed is given 70 meters per minute. Chip load is given 0.25 millimeters per tooth. What is chip load? Chip load is the load of the single cutting tool. A single cutting edge, I mean. It has got 22 cutting edges. Each edge takes a depth of cut of 0.25 millimeters when it is taking the cut. That's what it means. The load of each individual cutting edge. And then the cutting depth is also 5 millimeters. We need to determine the actual machining time, TM, to make one pass across the surface, and also we are to compute maximum material removal rate. Okay. Let's do part A first. I'm providing you with the solution to this problem. There is another problem after this which I would like to ask you to do it once you see the solution of this problem. Okay. What is given to us is cutting speed and chip load, which is F. The feed against each individual cutting edge, which is given that much. We are after TM, machining time, and also material removal rate. Okay. We are familiar with this equation from the past, and we had that in one of the slides. The relationship between cutting speed and the spindle speed. Okay, that's what we had in one of the slides. And because cutting speed is given 70 meters per minute, diameter is given, diameter of the cutting tool is given, we can easily work out the spindle speed needed in order to achieve that given cutting speed, which is that much. 279 revolutions per minute, or RPM. Okay, and then we've got to compute feed rate. What is given to us is only F, which is feed per cutting edge. In order to achieve feed rate, which is the feed per unit time, we've got to multiply the number of cutting edges, which is 22, MT, number of teeth, times spindle speed, which is computed up here, times chip load, which is also given in the statement of the problem. This does provide us with feed rate, which is the speed of motion of the machine failure per unit time. Okay? Now, when this is computed, the next step would be to compute offset length A. What's that? Look, we want to take a cut from here up to here, and the length is already given to us, which is 400 millimeters long. What we are after is machining time. When we have feed rate, the rate of motion of the table, and when we have that one, it should be easy, and we have got the length of the workpiece to be cut. It's easy for us to divide the length by feed rate to get machining time. That's what we did before, right? However, please note that in meaning there is a difference. The difference is that we cannot ask the machine to travel from this position to this position in order to perform the cut. We've got to travel a little bit larger distances from the two ends in order to clear the part. Does it sound right? The cutting tool has to travel larger distance before cutting begins. Then it touches the cutting tool, the workpiece, takes the cut, and it has to clear the part at the other end. So we've got to make the machine to travel a longer distance, which is equal to the length of the part plus 2 times A, which is the offset length. the center of the workpiece, the center of the cutter is at this position when cutting begins. You see, it is just when it is moving this way, when the workpiece is moving that way, it is engaged, and here it is engaged. Indeed, that's the workpiece in the beginning, that's the cutting tool in the beginning of the cut. Workpiece is moving along this direction. At this given point, cutting begins. And it has to travel all the way up to this point when the cut is completed and the cutting tool clears the workpiece. So we've got to compute 2 times A, and A for peripheral milling operations can be computed by making use of this equation, where capital D stands for diameter of the cutting tool and lowercase d represents cutting depth, which is 5 millimeters for this given operation. This is cutting depth, is given in the statement of the problem somewhere, which is 5 millimeters, it's given right here. And the diameter of the workpiece, which is capital D, is also given to be 80 millimeters. So, by making use of this equation, we can compute A. And eventually, once we are done with this, we've got to compute machining time, which is A plus 2 times A, divided by feed rate. Feed rate is already computed, right? So, that's the difference between this operation and turning that we had in the past, and also, say, drilling operation. Okay, now part B. What we are after in part B is maximum material removal rate during the cut. Why do we have word maximum in the statement of the problem? What is it representing, the word maximum? Well, what is meant by maximum there? In the beginning of the cut, please note that. In the beginning of the cut, at this time, cutting begins. But the rate of the material removal rate, which is material removed per unit time, is very small, because only a little bit of the cutting tool is engaged. And when this, the center of the cutting tool is just above the edge, front edge of the cutting tool, the full depth of the cutting tool is achieved. Meaning that material removal rate is not the same at all times. In the beginning, it is very small, then it reaches to a maximum, and the maximum material removal rate is kept in place until this point. And from this point again, material removal rate decreases. So maximum material removal rate means that when the cutting tool is fully engaged with the workpiece, and it gives us maximum material removal rate. How do we do that? By making use of the right equation, which is W times D. W is width of the workpiece times D, which is giving us the cross-sectional area to be cut, times the length of the workpiece, which is feed rate for this given example. Does give us the rate of material removal rate when it is maximum. Please don't forget that I have uploaded an equation sheet for you to be used for doing the problems. Have you got a copy of that with you?
Yeah.
Yes, that helps. Yes?
On the test of our exam, are we going to have these formulas?
You will have your own equation sheet.
Oh, we're allowed to bring in like
Yes, you will have to bring your own equation sheet. Write whatever you think is of use to you. Any comments on the parameters is fine. Write any comments that would help you in making use of the right equation, and bring your own equation sheet to the exam, which would be an A4 sheet. Both sides can be used, okay, for writing the equation. So bring your own equation sheet with you. If I want to attach all the equation sheet, there will be a lot, but you can just write it in a way that it takes minimum space so that you can write as many as equations you can. Okay. That's the equation sheet which I have uploaded, that one. That's the equation sheet. We have equations for turning, drilling, which we used it for the last lecture, and equations for milling are given here. It's on the blackboard. Everything is on the blackboard, yes. It's a good idea to bring a printed copy of the equation sheet with you for the 2 sessions when we are doing the problems. It helps, okay? So, the equations that we use for this problem. Listen everybody, please. The equations that we use is the spindle speed, which is similar in turning and also drilling. That's the one that we use, that's the one that we use, and that's the one that we use. Plus L plus A, which we use, and that one. We use all the equations indeed for this given problem, right? Look, here we've got A, offset distance for slab milling, which is also similar to peripheral milling. We've got another equation. Is everybody listening? We've got another equation for offset value A for face milling operation. You've got to make use of the right equation for the right problem. If your problem is talking about face milling operation, where the axis of machine tool is perpendicular to the surface weighing machine, make use of the bottom equation. If the operation is slab milling or peripheral milling, where the periphery of the cutting tool is taking the cut and the axis of the rotation is parallel to the surface weighing machine, then you've got to make use of the top equation of the two. That one for peripheral milling operations, when the axis of cutting is parallel to the surface weighing machine. This one is the other operation, when the axis of the machine is perpendicular to the surface weighing machine. You've got to know which one to use. Okay? Yes?
The equation here for the time which the cutting is engaged in the milling, it's Tm equals L plus T.
Yes. Yes. Sometimes A is 1A, sometimes it is 2A. You've got to know what is the base of the A to use. You're talking about 2A's or single A, right? Look, you've got to take a look at the operation and decide whether you've got a single A or 2 times A. You've got to know what distance is to be traveled. So the total distance would be A plus extra length. So it could be 1A, could be 2A. Sometimes people do compute one side and multiply it by 2 so they get a single A. A refers to extra distance to be traveled. That's what it is. Okay? By the way, it is telling you something. It's telling you A is the approach distance to reach full cutter depth. So it is only from one side. The other thing that I can tell you is that, let's go back to the problem statement in here. Look, please. The question was that in this equation we have computed 2 times A. In the equation sheet we got a single A. The difference is that if you consider a single A, it means that you are taking the cut from here all the way up to this point, when the center of the cutter is just above this edge. Indeed, cutting is completed. So 1 times A is right. However, the cutter has not yet cleared the workpiece. In other words, if you put a single A, you're right, it's not incorrect. However, you cannot remove the workpiece. The cutting is completed, it's not taking the cut anymore. In order to remove the cutter, the workpiece from the cutter, you've got to make it look a little bit longer. Okay? So 1A is correct. 2A provides you with the opportunity of removing the workpiece from the beneath of the cutting tool. If you consider 1A, still fine. Okay? 2A is also fine. Okay. Now let's move on to this operation here. Here we are making use of a face milling operation. Look, that one, face milling operation. The cutter is taking a cut from the start of the workpiece all the way to the end. Again, if we want to compute the same parameters for this given operation, Please note that in the beginning, we've got to make the cutter travel a distance A, which is the approach distance. And when the center of the workpiece is just at this point, right here, cutting is completed, right? However, the part is not yet clear, meaning that the workpiece is the cutting tool is still on the workpiece. You cannot remove the workpiece until you make it travel a larger distance and clear the area. That's not part of cutting. That's not part of cutting. If you want to compute the exact and actual cutting time, you've got to make the cutter travel from here to here. You're fine. But if you want to compute a little bit of extra distance in order to clear the part, again, it's fine. Nothing is wrong with that. But you've got to mention that I'm clearing the part. So I have considered another A on the other side of the, say, cutting operation. Okay. Now let's do one problem for face milling on the basis of what we just had. Okay. Here we are dealing with a face milling operation. A face milling operation is used to machine 6 millimeters from the top surface of a rectangular piece of aluminum, 300 millimeters long, 1 to 5 millimeters wide, and depth of cut is 6 millimeters as mentioned. It has to be done in a single pass. The cutter follows a path that is centered over the workpiece. It has 4 teeth and is 150 millimeters in diameter. That's the diameter of the cutting tool. Cutting speed is given. Please note that cutting speed is given in meters per second. It's not in meters per minute. Okay? You've got to take this into consideration. And chip load is given. We are to compute actual machining time to make the pass across the surface and maximum metal removal rate during cutting. Okay, take a note of those numbers that you need. I'm going to show you the equation sheet after this. So take a note of those parameters and numbers that you need. Then we will have the equation sheet on. For this given example, you compute A only once, okay? You compute approach distance only once. Don't consider it from the other end. Don't clear the workpiece from the part. Just the required approach distance, which is 1 time A. Have that one computed. This 6 millimeters given up here is the depth of cut, and the other parameters I think are clear what they are. What type of machine tool do we need in order to perform this task? This is face milling, is it? Face milling. Do we use vertical milling machine or horizontal one? Face milling means that the face of the cutter is taking the cut. It has to be vertical. It has to be vertical. Okay? That's what face means. It means that the face of the cutter is taking the cut. So when it is the face, it has to be vertical, otherwise it's impossible. Peripheral meaning means that periphery of the cutting tool is taking the cut. So it has to be horizontal. That's very clear. Okay, should I show you the equation sheet now? Yeah? Have you taken the note of this statement of the problem, which is also in your lecture notes, which I have uploaded? I don't know if you have access to the lecture notes. If you have, it's given to you in example problems, which I have uploaded. Okay, solution is also there. But it's a good idea to do the problem yourself before taking a look at the solution. Okay, the equation sheet for milling. You need the first equation for sure to compute spindle speed. And that's what we already know, right? V is equal to 5 times V times N. That's something that you are expected to know. Feed rate, which is spindle speed times NT. What does NT stand for? Number of cutting teeth times F. And material removal rate, which is W times D times FR. W stands for bits of the workpiece, D is depth of cut, and F is chip load. Sorry, FR is feed rate. And then Tn, F is the length of the workpiece plus A, which is the approach distance, and we've got to make use of the right equation for face milling. FR is already known. Which one of the two A's is to be used for this given problem? The second one, because it's a face milling operation. You've got to compute A to be substituted in equation 2017. Okay? I can switch to the other slide if you want to. Once you have taken the note of the equations that you need, I can switch to the other slide. Okay, I'm going to switch to the other slide. Okay, are you fine? Have you taken the note of the equations? Yes or no? Say something, please. If you have taken the note of the equations that you need, I'm going to switch back to the previous slide, which is the statement of the problem. What's the first thing to do? Spindle speed, as we had before, correct. So, spindle speed computation is the first thing to do. Because cutting speed is given, diameter of the cutting tool is given, so it's easier for us to compute spindle speed. Please note that what is computed here is revolutions per second. You can multiply it by 60 to get revolutions per minute, which is fine. Or maybe you can do the conversion of it in the very beginning. It's up to you, the way that you want to do it. What we want to have is a right proper unit at the end of the problem. Okay? So, now what spindle speed is computed in revolutions per second, that's why we have got such a low number. Then, we've got to make use of the feed rate equation that we had in the previous slide. We've got N, we've got NT, and we've got F, which gives us 6.42 millimeters per second again. This is not millimeters per minute. Next, what do we do next? Computation of A, which is right. Which equation? Face milling equation. The top equation. The bottom equation, sorry. The bottom equation, where capital D stands for diameter and W stands for the width of the workpiece. Okay, substituting all those numbers, we can compute the approach distance, which is A, and then it's easy to compute Tm because we've got L plus A divided by FR. And please note that here we have got, because we had per second and per second, we didn't do the conversion of the units, what we get for Tm is seconds. Okay? Then we got to divide it by 60 to get minutes. So this is what we are after in the end. Time in minutes. So it's up to you how you want to do it. In the end, we've got to get time in minutes. And material removal rate now. Well, we've got the equation, we've got all the parameters. It's not hard to have this computed, right? Just substitute right values in order to get that. What is this for standing here? This for, what is this representing? Number of cutting edges, which is empty. And it is given in the statement of the problem. It has got 4 cutting edges, or 4 teeth. Okay? Any problems on this? Any questions? No. I know machining is very easy. Machining problems are all easy, right? All you need to do is just to do a number of problems in order to know which equation to be used in the right place. That's it. And I can tell you that there will be one problem from machining from these 2 lectures in the final exam. That's for sure.
Only one.
We will have, I think, 4 problems. I don't think we can have more than 1 problem from 2 lectures.
Oh, sorry.
Okay? You will have 4 problems and 40 multiple choice questions to do. 40, yes.
Are they going to be theory?
Yeah, in the final exam, okay? In the final exam. You will have 40 multiple choice questions plus 4 problems. And you cannot have more than 1 problem, machining problem. Because we've got so many other lectures as well.
Is the final exam theory as well?
Final exam is a combination of multiple choice plus problems. Multiple choice questions from teaching materials plus some problems. 40 and 4, that's what I have in mind. Okay, I haven't made the questions as yet, but that's what I often do.
Yeah, and we are allowed to bring
Equation sheet, you can bring your own equation sheet with you. Only equation sheet, okay? Not lecture notes, not summary of lecture notes, only equation sheets. You can bring an equation sheet with you. Okay. For the mid-semester test, which is due next week, I think I have sent you information. Everything is in it, right? Everything is made clear, no problems, just some multiple choice questions to be answered. And I assume those questions are familiar to those who have been present in lectures, most of them at least, if not all, are already familiar to us. I'm not bringing some questions from other planets. It's all questions from the lecture notes. So it should be familiar to us. But anyway, it's a good idea to read the lecture notes and also the textbook if we have sufficient time. There could be some questions from the text to distinguish between those who have gone through the text and those who haven't. It won't be many, but there could be some. Okay. I think it's the time for a short break. Okay? Take a short break for 10 minutes and we will continue afterwards. Okay, let's continue with what is left. Could I ask you to take your seats, please, everybody? Well, let's begin what is left of the lecture with this question. What are two operations where no rotation of the cutting tool or the workpiece is involved in the cutting process? Can we name any machining operations where no rotation is involved? Either the rotation of the workpiece or the cutting tool. Yes? What's that?
Brushing.
Broaching, you mean? Broaching is right. We had that before, broaching. You remember that? The hole, which I'm going to talk about it later on, where a hole is made and a cutting tool passes through the hole and leaving its geometry on the hole, on the external surface of the hole, which providing us with different shapes. We have some pictures from broaching operation. That's one. What else? Yes? What's that? Quenching? Punching. Is this considered as a machine operation punching? We don't normally consider as a machine operation. It's wrong, but it's not a machine operation. So, what else? Shaping, yes. Do you know what shaping is? Shaping and planing. These are the two that I was after, but also there are some other methods, including broaching, which are right. Shaping and planing. What does that mean? In shaping and planing operations, there is a single edge cutting tool which takes the cut when it is moving linearly. And the workpiece, even it's stationary, it is either stationary or it is moving along a straight line. It does not rotate. Well, as you can see here, in A we have got shaping operation, in B we have got planing operation. They are very similar, aren't they? But there is a big difference between the two. And what's that? The difference between the two? The feed motion, which is right. Here, in shaping operation, feed motion is being applied to the workpiece. But in the other one, the feed motion is being applied to the cutter. There is another difference. The other difference is that in shaping, excluding feed motion, it's the workpiece which is stationary, and it's the cutting tool which makes the reciprocating motion, just like that. Just like that. It's the cutting tool which moves linearly to take the cut. However, in planing operation, it's the it's the cutter which is considered as stationary, excluding the feed motion, and it is the workpiece which is moving. That's the main difference between the two. The feed motion and also the reciprocating linear motion. In both operations, a single edge cutting tool is used. In both operations, no rotation is involved. Let me show you the pictures in the next slide. The pictures of the two machines, as you can see. That's a shaper which is used for shaping operation. And here we've got a planer which is used for planing operation. In here, as you can see, there is a small table. The workpiece sits on the small table. And the feed motion is along this direction. And it's the cutting tool which is moving back and forth to take the cut. Right? It takes one cut, and then once it takes the cut, returns to the initial position, which is back right here. Then the table makes a small motion, which is the feed motion, by separation of a millimeter or a couple of millimeters sometimes. It makes the cutter move, the workpiece move along this direction. The cutting tool then takes another cut. Again back to the initial position, another feed motion, another cut. And it keeps going just like that until the whole surface is cut. How about the planing operation? In the planing operation, as you can see, there is a rail mechanism, and the table of the rail mechanism moves back and forth. And the cutting tool is on a cross rail which can move on the rails from one direction to the other. So when the workpiece makes a full motion, a cut is taken. Then the feed motion is applied, moving the cutting tool a little bit to the left for the next motion by a few millimeters only. Another motion, another cut. Then another feed motion, another cut. And eventually the whole surface of the workpiece is cut. Shaping operation is used often for relatively small workpieces. Planing operations are used for relatively large workpieces as its able competition. Okay? So as you can see, we can do the machining without involving any rotational motion, which is possible. However, please note that in the beginning of the motion, the speed of motion is 0. At the end, it's also 0. So we've got to increase the speed of motion from 0 to maximum and again lowering to 0. And this cycle is being repeated every time. Is this an efficient way of machining? Maybe not. However, for majority of surface machining operations like these ones where you are to produce a flat surface, these two methods are the least expensive machining methods. Planing and also shaping operations are relatively low expensive machining operations compared to milling, which can produce the same surface. Reason? Cost of tooling is really low. We've got a single cutting edge in these operations, and the cutting tool can be made easily. When you are making use of milling machines, you've got to pay for the high expenses of the cutting tool. And also the machine tool is more expensive. By the way, material removal rate in these two operations is significantly greater than milling. As a consequence, if we are to produce a lot of flat surfaces, it is more economical to make use of these two operations instead of milling. Okay? Anyway, you can achieve a really good surface finish by making use of this operation. Really good surface finish, making it. The advantage of milling, what's the advantage of milling then? That's a good question. Milling can be used to produce a variety of shapes, not just flat surfaces. But these processes can only be used to produce flat surfaces. We have examples of milling operations. You can produce a variety of shapes on milling machine. On this one, you can't, of course. Only flat surfaces can be produced by making use of these two operations. And broaching, you refer to broaching. Take a look at these figures here. You've got some shapes, internal shapes. And they are different from one another. Very different from one another. One of the operations makes us able to make these internal shapes at relatively low cost. What's that? Broaching. What's that? In broaching operation, as you can see in this figure here, first of all, you've got to make a round hole by making use of a drilling operation or something like that. You make the round hole. Then you make a cutting tool which is called broach, just like that. And it has got multiple cutting edges. Not two, this is just a section of it. It's really large. And it has got a large number of cutting edges along the lengths. You've got the round hole and you want to make these slots on it. What you do is that you pass one end of the broach from the end of this. You put the flat surface, indeed you put the workpiece on the top of the table, just like that. It has got a hole on it. Then you pass the bottom end of the broach from the hole, and it is grabbed in the bottom in a fixture. And eventually the whole broach passes through the hole. The first edge takes a very small cut. The second edge makes a larger, make the depth of the It's not larger, and eventually what is left on the whole is the geometry of the last cutting edge of the broach, which is shown here properly. You can see this is the whole length of the broach, and this is the way that it is taking the cut. A very small depth of cut in the beginning, and the depth of cut becomes bigger and bigger and bigger, cut after cut, or edge after edge. Eventually, the geometry of the last cutting edge is significantly greater than the difference of the geometry of the first cutting edge. Just like a hacksaw, every cutting edge takes a very small cut. But when the whole edge works on a piece of workpiece, it takes a really big cut. By making use of this method, you can make very different types of workpieces. Take a look at these examples here. Those surfaces which are cross-hatched are the surfaces which are produced by a broach. And as you can see, we can make use of broaching operation not just for internal shapes, but also sometimes for external shapes as well. The advantages of this method. This is a very efficient method because of low machining time, and also it does produce really fine surface finish in the end of the operation. And very precise geometry can be achieved by making use of this operation. However, the cost of tooling is high. The broach itself, we've got to order it for any specific shape that we want to produce. And the cost of tooling is high because a number of cutting edges are to be produced along the length of the broach. And that requires special cutting tools, special equipment and machine tools, and also skilled people to design the broach and also to make it. Okay. Any questions on this? It's interesting, isn't it? It is. I agree. Sewing, I think we know about different types of sewing machines, right? Mechanical sew, hacksaw, and continuous ones, and the disc hacksaw, disc hacksaw, which I'm not going to talk about it, which has got a saw blade. So I'm just skipping this. Okay. This is a familiar slide, right? That's what I did show you in the beginning of previous lecture. Now, what I'm going to ask you is to go to your partner, the one who's sitting next to you, and do actually assign a number of machining operations that can be used to make each of the workpieces shown here on the basis of what we had in the last two lectures. You can now mention a number of methods that can be used to make each one of them. List those operations that can be used in order to make each of these workpieces on the basis of what we discussed. Okay? Spend a couple of minutes on these before we move on. Go to the SSP next to you, okay? That's what I wrote there. To assign more minutes for Okay? Have we made any progress? Yes, we have. Good. Number A. What operations can be used, what machining operations can be used in order to make part A? Shaping. Can we make use of shaping to make this part? Yes or no? Well, it is possible, but we've got to be very actually expert in order to do that, because shaping starts cutting from one side and terminates the cutting in the other end of the surface. Here we've got a little bit of protrusion left at the corners. If we are a good machinist, we are able to make use of planing and also shaping to make this part. But not everyone can do it. Milling is the preferred operation for this if you are not a really good machinist on a shaping machine or a planing machine. But anyway, we cannot rule out shaping and planing operations for this part. Any other methods other than milling? Of the conventional methods, I don't know any other method which can be used. Milling is the most preferred option, and of course shaping and planing cannot be ruled out. Okay, part B. Milling, yes. Shaping. Let me see. How can you make it with shaping method? It's not easy to make it on a shaping machine. How can you make it? Because you've got gears, straight gears on it. If you can reset the amount of feed properly and you've got the same geometry on the cutting tool, it might be possible, but I see it really hard, frankly. Because reason is that it makes only a small distance motion along the feed direction. In here it has got to be a very exact distance to be traveled to move from one slot or one gear to the next. I see it really hard. I am not saying it's impossible, but if it is, it's not an easy task. I wouldn't do it. I wouldn't do it. So again, milling. What type of milling? Face milling or peripheral milling? Peripheral milling, right? Because a horizontal milling machine has to be used in order to make this part, and the cutter has to have the geometry of the gears. Okay. Vertical milling, how can you make it? You've got to, you've got to actually put the workpiece just like that along a vertical workpiece. I don't see it possible. Oh, this way, this way. This way, you are moving it this way and taking the cut like that, right? Yeah, it is possible. It is possible, but of course horizontal milling machine would be easier. But it is still possible on the vertical milling machine. Well, any other method for making part B? Other than milling? Broaching can also be used, yes. Broaching can also be used where we've got the shape of the gears machined on the broaching tool. Starting from one end, going all the way to the other end. Broaching is other possibility, right? Yeah, for the first one also, yes. Broaching can also be used for the first part as well. But of course, it's more expensive than milling. Okay. Face. For which one? For which one? For B. What was the method that you mentioned? Face? What's that? Face grooving, you mean? I don't know what you mean by this. Let us have a chat later on, okay? Let us have a chat on this. Then I tell you if it works or not. Okay, part C. For the pocket, we've got to make use of an end mill, which is pocket milling. Okay, for the pocket, for the cavity inside. For some other places, we've got, for say this corner, and for that one, we've got to make use of, no, not the hole, this edge, this notch indeed. And for this pocket, we've got to make use of end milling as well, and also this cavity. For the holes, we've got to make use of drilling, of course. And for the slots in here and also in here, we've got to make use of a vertical milling machine or a horizontal milling machine as well for slot cutting. So milling is the preferred operation plus drilling. For that one, of course, the rotational part, turning. How about for this slot here? For this slot here, milling. And for the holes, drilling or what? I would say a mill turn center would be an ideal machine to produce this part. What is it? That's what we are going to have just after this slide. A machine which can perform milling and turning at the same time, not at the same time, on the same part, in the same machine. We will have a video clip on that as well. This one, which is a gear, turning, yes, and drilling. You are talking about the hole, right? Drilling on the turning machine, yes. How about the gears? What method? Broaching can be used, yes. What else? Milling. Milling is frequently used for machining gears. No, it won't. Indeed, there is a machine which is called dividing mechanism. It has got a actually rotational axis which holds the workpiece, and once one part is taken, workpiece rotates one step, and another part, and all the way the whole workpiece is cut, which is the gear. So it's very quick when you make use of the right equipment to do that. Okay, let me finish with the last one, and then I will answer your questions. And the very last one, which is F. Correct. Face milling? I wouldn't say so. You can. I don't know. Sometimes I can never rule out something because sometimes there are some machinists who are really expert and creative, and they do the things that you can never think of. Like what? Doing milling on a lathe. I've seen it. Some people do milling on a lathe. That happens, yes. They do milling on a lathe. How do they do that? I've seen it. They make use of the spindles and mount the milling cutter on the spindle, and they put the workpiece on the support of the machine and make it move linearly when it's taking the cut. It's milling which is being performed on turning. So these things happen, and things like that I've seen a lot. So some people do things which is with a machine which is not designed for that purpose. But things like that happen in industry. So when he says that we can make this with milling, I'm saying that I don't think that way. He says that I can, I will say you can. I wouldn't, believe me, because I've seen people do things that look impossible in the beginning, but they do it.
It's a special tool, it's weighted so that it actually square hole.
Okay. Maybe we can have a chat on this later. Tell me how it can be done, okay? Anyway. Okay, now we are done with this. Let's move on to computer numerical control, just an introduction to. In computer numerical control machines, what happens is that a computerized system is used in order to send commands of the program of a program which has been developed for a specific part. A programmer develops the program, and then the program is entered into the machine control unit, and it is being executed on the machine block by block or line by line. Each block is providing the machine with a specific piece of information, and when the whole program is executed, those blocks do define the motion of the cutting tool and the workpiece, and eventually do control the process. And after all, what is left is a part which is machined. And generally, the precision of CNC machines is 10 times greater than conventional machines. Sometimes less, sometimes more, but it's safe to say that it is 10 times greater by 1 digit. So what we achieve from CNC machines is a part which has got a higher accuracy compared to conventional machines. However, please note that they don't do miracles, meaning that sometimes there is a very complex part and you ask people what machine can produce this, they say CNC machine, thinking that CNC machine can do whatever they want. No, that's not the case. CNC machines can perform what conventional machines can do, however, productivity is higher, precision is higher. That's the difference. Otherwise, they are not very different from conventional machines. Okay, what we see here in this slide is a CNC machining center. As you can see, there is a magazine here which holds the tools in place. And that's the spindle which holds the place and rotates which holds the cutting tool, and it actually cuts the material. Those cutting tools are taken from here. As you can see, it can hold a large number of cutting tools in the magazine. And there is this mechanism in place which actually replaces the cutting tool which is on the spindle with the one which is in the magazine. So when you've got a large number of cutting tools available, and for any given machining operation, the right cutting tool is used. Tool changing is automated. Everything is automated indeed. And that's why there is minimum amount of time which is not being used for cutting the material. And for this given machine, as you can see, we've got a shuttle. We've got two actually positions for placing the workpiece and the fixture, one in here, another one here. Meaning that when one workpiece is being machined, another workpiece is being removed from this fixture and another raw material will be placed. So that once the machining of this one is completed, what happens is that the machining center just switches the places of the two workpieces. The one which is machined comes to this place, and the one which is new raw material is on it goes to the position of machining. So that the time which is spent on loading and unloading of the workpieces on the fixture is not lost. And machine is doing the machining at all times. And this is another CNC turning center which you can see. We've got two supports, and each of the supports holds a number of cutting tools. We've got the spindle, which holds the workpiece, and there is a robot here, which is used in order, which is used for loading and unloading of the workpiece on the chart, in order to automate all the activities, including loading and unloading. And here we can see a part which is machined on a mill turn center. What does that mean? It means that essentially it has got the structure of a turning machine. However, turning machine is not able, conventional turning machines cannot do milling. In a mill turn center, not all the turning CNC machines can do the milling, but those which are mill turn CNC machines can perform turning as well as milling on a given workpiece. What happens is that workpiece is being machined on the turning machine, the spindle is rotating. And eventually, the spindle is locked in place when the milling cutter comes next to it and takes a cut in order to produce the flat surface. And also, the same mechanism is used in order to make a hole on it. Meaning that if we are machining a rotational part, and there are small features of milling and drilling on it, we don't need to make use of a second machine. The same machine can be used in order to perform the whole task. However, the amount of milling and drilling is limited, because generally it is a turning machine. And when this is the case, the time required for actually loading and unloading of the workpiece from one machine to another machine is eliminated, because the whole task can be performed on the same machine. And this also increases the accuracy of the workpiece, because when you unload the workpiece from one machine and load it onto the other machine, there is some error in positioning in the next machine, which results in what you achieve, which results in some inaccuracy in what you achieve. So we've got to reduce the number of loading and unloading of the workpieces in order to improve the accuracy and precision of the part which is made. So this given part is machined on a mill turn center without making use of two different machines in order to make it. Okay? Those who will be doing advanced materials and manufacturing next semester, we will be doing programming of CNC machines on it, and we will go through details of the CNC machines. Not in this unit, but anyway, here we are just having a very brief introduction on CNC machines. Okay, any questions on meal term center?